So here we are, properties of gases and principle of combustion. So please stop me anytime if you have any questions, okay? Please, and then I'll, try to give some clarity to what this is saying. It's got a lot of colors. It's got a lot of, not animations, but a lot of colors. So if anybody starts in a some kind of epileptic fit after all the colors, then, we'll slow down.
Hey, Doug, is this it?
What's that?
Sorry.
You have the PowerPoint, Josh?
This is it, yeah?
Yeah.
Oh,
Was
sweet,
that,
yeah.
how did you get that? Did you print it?
I was in class last March.
Oh, right, right. So
Yeah, I've done
Is
2 weeks of this, so
copy.
is this the colossal PowerPoint? I think I've got that downstairs.
It's like 100 slides, Toslin. Yeah, it's 100 slides. So it's weighty.
I've got
I don't
57
recommend you. I
pages.
do not recommend you print this. This will suck all your printer paper completely dry and your ink. Okay, so I don't recommend printing it. Okay. Here we go. The objectives laid out with this follows the ILM, the 0800103E. It kind of really follows it exactly, I should say. So we're going to state chemical formulas. We're going to talk about relative densities, liquefaction ratios, whatever the heck that means, heating values, various trade-related problems. So we're going to do a little bit of math, and that's for you, Farid. Identify definitions specific to combustion. Explain principles of combustion, chemical changes. Talk about combustion air, which we did yesterday, but we're going to revisit and add more to it, hopefully. Describe flame adjustment techniques, and that's a little bit of troubleshooting in there as well. Okay, number 1, state chemical formulas. Pretty easy. Methane, a hydrocarbon. You see it has 1 carbon molecule in the middle, 4 hydrogen on the outside. CH4. Yeah? So it says here, to fully understand physical characteristics, we must identify. Okay, whatever. The smallest particles is the atom, right? All matter is comprised of atoms. That's pretty straightforward. We know that already. And then they say there's approximately 118 elements known to man, or atoms. And that is of 1 element. Pretty straightforward. Now, how can there be tens of thousands of different material available? Well, everything gets combined and we make up new things, and nature does that all by itself too. So some molecules, such as oxygen, are made up of 1 type of atom. But when they get together, they make a compound, right? And that's what they're trying to say. And they bond together, really super high, strong bond when they come together. And that bond is all about how that atom's electrons floating around the outside stick to one another, right? They have an attraction for one another. It's like when you have an attraction for another person. It's just one of those things. It's just you want to stick together. Okay, and then there are more types of molecules than are atoms, and most matter will be made up of these atomic cocktails. And I don't know why they call it a cocktail and they show a cup of coffee here, but that's too bad. Should have had a rum and coke there. We've already determined that molecules can remain as elements, but when you get some things called a mixture, is 2 or more types of atoms, like putting sugar into your coffee. And I've given up putting sugar into my coffee, by the way. So it'll help my weight loss because I've been eating too much sugar sitting on my assets here at home. So, a compound, on the other hand, it's a definite ratio. It means that when some of these atoms come together, you have a compound. Like this hydrogen or this methane molecule and is a compound. It has carbon and hydrogen together, and they form a pretty strong bond between each other. Okay, and we know these as hydrocarbons. Any questions so far? We are flying through this because this is not new. We should know some of this stuff. And here we have a different slide showing these compounds. Now, butane and isobutane, they're very much the same. These two are very much the same. They just it has a little bit of different makeup in their chemical bonds. But they are C4H10, both of them. Butane and isobutane, we're gonna consider them the same. Now, in our trade, we deal mainly with methane, natural gas, or propane. Okay, now they show this little table here just for comparison purposes. So this is the percentage of gases, or the percent of what's in these gases. Okay, there's a little bit of coal gas and all kinds of things. So, you know, to have a pure substance is pretty hard, quite frankly. The next table, or the next slide, again, it's just providing us with an idea of what the makeup is. So when discussing properties of a hydrocarbons, we need to know the physical properties of the liquid, the physical properties of the gas, and combustion characteristics. And remember, we're only really going to do methane, excuse me, and propane for the most part. Okay, to define properties of hydrocarbon groups of gases, okay, we're going to look at solids. Down here in the red, solids are a state of matter, definite shape, volume, and weight. Okay. Liquids, they really have a definite volume and a definite weight, but they don't have a shape of their own. They will take the shape of the container that they are in. This is from first year. Solids. Now, we won't talk about plasmas here, right? We only do the three states, solid, liquid, and gases. And here's vapors or gases. They have no definite shape or volume, but they do have a mass. All matter has a mass. And we can compress gases, can we not? We cannot compress liquids. I mean, we can keep them under pressure, but we can't actually squish them into a smaller space. Okay, so there's two factors that influence the state in which matter exists, and that is temperature and pressure. We should already know that. And of course, ice, or as a solid, will change into a liquid when heated. And also, water will change into a vapor or a gas when there's even more heat applied. So matter can be changed from one state to another and even back again, because we can get it all going backwards as well if we put enough pressure on there. So, as we're moving more forward, water at 14.7, that is atmospheric pressure, boils at 212. Yeah, that makes sense. While water at 1 psi, now I want you to see this top sentence. Once we start adding pressure to this liquid, what happens to the boiling point? You see what happens? It goes up. The boiling point goes up if I put a liquid under pressure. Okay? Especially water. See, as you can see here, water at 15 psi. So if we have it in a closed situation, we can get that water to boil at 250 degrees Fahrenheit. Meaning the more pressure, the higher the boiling point. Make sure you make a note somewhere on your paper of that. And of course, on the other side of it, once you have less atmospheric pressure, the boiling point is reduced, right? So the higher we go on a mountain top, the higher elevation we go, the boiling point is less than 212. So they say here, if enough pressure is removed from water, it will boil at room temperature. Okay, well, that's if we're in outer space or something. I mean, I don't know how to, you really got to get some kind of vacuum going there. Any questions? No. Okay. Now, hydrocarbons can be further subclassified into liquid petroleum gases, and we call those LPG. Liquid petroleum gas, LPG. And it's a group of hydrocarbons that can exist at either liquids or gases at relatively low pressures and normal temperatures. Does anybody have a lighter on them? A little lighter? Anybody? Any smokers? Hey, Ben's a smoker. No, maybe. So if you notice inside lighters, there is only a certain amount of liquid, right? There's only a certain amount of liquid inside lighters. I always thought I was getting gypped, but here's the thing, is that we burn the vapor and not the liquid. So there always has to be a vapor space in these containers. Even propane containers and even your butane lighter containers, there always has to be a vapor space because we burn vapor only. We burn gas only, not liquid. That's why there's always a space for them there. And these common LPGs are propane and butane. Okay. It goes on to say down at the bottom here that acetylene is not considered to be an LPG because it is dissolved in acetone for stabilization. So this other table that they have up here, it says methane will change its state from a liquid to a vapor at minus 258 degrees. What? So that is the boiling point of natural gas, meaning you have to have it under very high pressures to keep it a liquid. Propane here, minus 44. Butane, 32 degrees. That is the freezing point. So Ben, when you're outside trying to light your smoke in the very cold weather, your lighter doesn't work, you got to warm it up. You got to rub it in your hands, right? You got to, before you light your smoke, because you got to heat that up above the freezing point outside. Okay. Temperature does change the state of matter. It depends how much temperature you have, though. Pressure will influence the temperature. So when pressure is increased, the boiling temperature will increase. And so that's what they're trying to say here. It's pretty straightforward. And next, the boiling temperature of these LPGs, liquid petroleum gases, depend upon the pressure exerted. So, for example, the boiling point of LPG is usually stated at standard atmospheric pressure. But let's have a look at this table down here. It says if you put propane under pressure 23.5 psi gauge pressure, look at what happens to the boiling point. It's now at 0 degrees. So that's all we have to do is put it under pressure and we can get the boiling point higher. And then it gives you a whole list of pressures here. So propane at atmospheric pressure has a boiling point of minus 44. Normally, propane liquid in a closed container will be at the same temperature as the surrounding air, right? So an increase in the temperature will result in increase in liquid temperature, which would cause propane to boil off. So this propane pressure increases until the pressure is sufficient to stop the liquid from boiling. So inside your propane tank, you would actually have boiling liquid until it pressurizes enough to stop it from boiling. And that's how we use this particular gas. As we burn it in whatever appliance we have, it will peel off the pressure off the top in the vapor space, causing that pressure to go down. The liquid would boil, making more vapor. So it's a whole cyclical thing. And then when you shut off your appliance, it will continue to boil inside that container until the pressure is sufficient to stop the liquid from boiling. We have a clear glass propane container that we could watch the propane boil, and we'll do that when we're in Gas Lab in the coming weeks. Okay, we'll have a little demonstration on that. So here we are. It's going to just describe exactly what I just said. When there's demand for gas, the pressure in the tank drops. So downstream of this first stage regulator, we're going to be using some of that fuel for space heating, for cooking, for whatever it is that we're using it for. And inside this tank, the liquid boils and expands 270 times its original volume. That is an important number that you need to know right there, 270 times. We know water expands, approximately 1,700 times? Propane liquid will expand 270 times its volume. And the next slide just shows a temperature comparison between water and propane. Okay, the one on the left is propane, the one on the right is water. I'm not going to talk about this too much. I mean, whatever. We don't need to memorize any of that stuff. There is a couple of numbers on here that are important. What is the boiling point of propane at STP? You should know that. What is it, minus 44? Right. Okay. So that was objective 1. Boy, you guys are pretty good. Thank you for paying attention. Thank you for staying awake. It's important that you stay awake. State the relative densities, liquefaction ratios, heating values of gases in both imperial and metric units. Here we go. The weight of anything is dependent upon the a certain number of variables. So standard temperature and pressure is used when we make any comparisons, right? And we know what standard temperature is. And this slide is wrong. What is the standard temperature for metric? 15.5 degrees C. They put 0 in here for some reason and never changed it. So that number is incorrect. And the standard pressure is 14.7 or 101 kPa. So we know that already. I think I've talked about enough of that.
Sorry, Doug, the edit for this is
15.5 degrees Celsius is standard temperature for metric, not 0.
Okay, cool. Just because I saved it to my computer, so I'm just gonna change it.
Okay, yeah, it needs to be adjusted here. Yeah, this is that. Okay. Now, density. You should have learned a lot about density in your first year and even your second year of apprenticeship. Here we go. We have a bunch of things the same in this picture, but they're all different densities. Some are heavier than others. Each sample is not exactly the same, but you can compare them because there's different materials, thicker walls, heavier, thinnest. I don't like this slide. It's not very good. But if we were in a shop class and I had all those pieces of pipe with me, then it would be a better comparison. Now, the relationship between the volume and the weight of the substance is called density. We know what density by definition is a substance stated in a weight per unit of volume. So pounds per cubic foot, pounds per cubic inch, kilograms per cubic meter. Yes, we know that. Here is a density of 1 imperial gallon. It's 10 pounds per gallon. Okay? So to say 10 or 10 pounds would have no meaning. The correct way is 10 pounds per imperial gallon. Okay, this again is old stuff. You should know how to do these. There's some water densities. I think we wrote those down at one point. I think at the beginning of our Monday, I think we wrote these down. Next, here's densities of other various materials. Yeah, so what you could do is you can just divide by the standards at which these are. For example, you see where mercury is? It has a density of 848 pounds per cubic foot. And if you divide by the standard of water at 62.4 pounds per cubic foot, you will find the relative density of mercury. And it should come out to about 13.6. Any questions? Is everybody getting it? Yeah, it's pretty easy stuff so far. Okay. Okay, so here is the density triangle. Mass, density, volume. So density is mass divided by volume. We'll use this formula to do any of those. That is, again, old stuff. So the term relative density or specific gravity is just a comparison. We want to know how many times heavier or lighter a substance is compared to our standards. And our standards are water and air, right? And they're both given a 1. And everything is either heavier or lighter than the standard. So how many times heavier or lighter is these particular things? As a liquid, butane is 0.58. As a liquid, propane is 0.51. Methane is 0.424, meaning that they are all lighter than water. Yes? All of them are lighter than water. If you dumped these liquid products into water, it would float on the top. Mind you, it has to be pretty damn cold, though, to get them in liquid state. So those numbers, the bottom two, the ones that are in bold letter in this little table, are really the ones you should kind of know. Oh, wow, what a transition that was. Propane liquid has a specific gravity of 0.51. I don't care about the other number there. I don't even know why they put it in there. Therefore, if 1 gallon of water weighs 10 pounds, then 1 gallon of liquid propane would weigh 5.1 pounds. Right? That's exactly what it would be, because we just take the relative density and multiply it by what the standard is. The standard is water, and then we just multiply it. Again, 1 liter of water weighs 1 kilogram, then 1 liter of propane weighs 0.51. And there is how they got those numbers. Okay, now, if liquid propane were to spill in a bucket of water, it would tend to float on top. But it would have to be at minus 44 degrees Fahrenheit for you to be able to do that. So once the liquids are vaporized to gases, they adopt a new selection of properties. So here is the vapor and specific gravity of these vapors. So propane has a specific gravity, and this is a gas. Propane gas has a specific gravity of 1.5, meaning it is heavier than air. And this is the reason why you cannot park a propane vehicle in an underground parkade. Next time you go into an underground parkade, just see there should be some signs, and it will say no propane vehicles allowed. Because if that vehicle had a leak on it of some sort, guess where all that gas is going to go? Down down to the lower levels.
But if you have a makeup air unit, wouldn't that solve that problem because it keeps the air cycling?
Oh, sure. Let's just propane gas and blow it all around the place then. No. It's bad, okay? It's bad if it has a leak. So that's why we're not allowed to have propane vehicles in underground parkades. All right. So it says natural gas methane has a specific gravity of 0.6. So when it's released into the room, it rises to the ceiling. Now, how do we know what gas that we're dealing with? How do we know? Because natural gas and propane gas are actually colorless and odorless. How do we know that there is gas in the area? Does anybody know?
Or Captain?
That's right. They add something called mercaptan to it. And let me just write that down if I can. I don't even know. I lost my writing stick here. There it is. Mercaptan. So you see it at the top of the page there? Mercaptan. So propane and natural gas actually smell different from each other. If you don't know that, they do. And it is the amount of mercaptan that they put in them. And we'll at some point, maybe not today, but at some point we'll find out how much percentage of mercaptan they dump into. So they put in certain amounts, and so they smell differently. And this is an indication that there is a leak. If you smell gas, there's a leak somewhere. Okay? And if it's grandpa, well, he's leaking all the time. There's no question about it. Or, your significant other. And quite frankly, it's natural, so it's not that, Okay. Questions? You guys are the best. Oh, let's go clear. All right.
Hey, Doug,
Yes.
what was the relative density of methane as a liquid?
As a liquid, 0.458, I think. Let me go back here. Oh, 0.424. Sorry. 0.424. And then we get to propane gas as a specific gravity 1.5. So it's 1.5 times heavier than air. This is a little air weighs 0.076 pounds per cubic foot. So we just made the assumption of what 1 cubic foot of propane gas weighs. And it comes out to, there we are, 0.144 pounds per cubic foot. And that is the mass of propane gas. It's a comparison. We're good? Got that? Excuse me. Okay. Oh my gosh. See that propane tank down there and see those firefighters in there? What a dangerous situation that is. Man. One ignition source there, and those guys are TOAST. They are toast. That's pretty awful. So if a propane gas were to leak out of a pipe in a room, it would tend to concentrate on the ground. The other stuff would tend to rise. Has anybody seen a BLEVE? Does anybody know what a BLEVE is? A BLEVE is a boiling liquid evaporation vapor explosion. I think we need to see a BLEVE here.
Is that something we should be writing down as a note, or?
Sure.
Okay.
Hang on a second here. Whoa, slow down.
Will BLEVE be on a test?
No, probably not. Okay, let's have a look at what a BLEVE is. Now, those firefighters that were underneath that propane tank trying to fix a leak is pretty bad, but here we go. Oh, sharing the wrong screen. Why don't I share the screen that I want to share? Here we go.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly and with little warning.
Craziness ensues. I wouldn't want to be a firefighter around propane tanks. Let me tell you that. You're going to want to be a long ways away from any one of those. That's absolutely frightening, to say the least. So firefighters, when they go to fight fires in apartment buildings, they get concerned because you know what people do? They put propane tanks on their balconies, do they not? And so that relief valve on those propane tanks is universal. And it is set at about 350 PSI. You could write that down. The relief valve on a propane tank is about 350 PSI. So when these tanks get heated by outside heating source, that pressure is allowed to increase. The relief valve opens, bleeds off a lot of pressure. And again, the liquid starts boiling again because the liquid pressure is reduced. And it just keeps going until it blows up. It's frightening.
And sorry, that was 350.
That's correct.
Thank you.
Yeah. Okay, we're going to go through a few more slides before we take a break. So we'll back at it. That was my little side note on propane leaks, because I don't like leaks of any sort.
Then in theory, if your safety relief valve was blowing, that would give the firefighters time to put the fire out before the whole tank blew up?
I would hope so.
Okay.
Okay. But you know what? We carry propane, isobutane, etc. on rail cars, don't we? Yeah. And when rail cars crash and start on fire, they just have to sit back and let it burn out. There's not a lot they can do. You don't want to get close to that. It's pretty awful. So if anybody's got, wants to, I don't know. I don't like rail cars full of propane liquid running down in the middle of downtown Calgary. I don't know why we have train cars running in the middle of downtown.
Because we're not allowed pipelines, but we'll dump sewage into rivers and oceans.
Okay, thanks for that. We'll talk about plumbing theory next class. Okay, few more slides before we take a break. Hang on a second. Here we go. Okay, the number of cubic feet of gas at standard temperature and pressure will condense into a given unit of volume of liquid is the opposite of vaporization. So this is propane will expand 270 times for every 1 cubic foot. Okay? And 1 cubic foot per gallon. So you get, for every gallon of propane liquid, you will get 43.6 cubic feet of vapor. Okay? So those two numbers right there for just propane. I'm not going to be really concerned about butane, but the propane numbers right here are the ones you need to know. The next slide. So this liquefaction ratio, will it be expressed in cubic feet of gas? So we're talking about the gas per volume of liquid. Okay? So 1 gallon of C3H8 in this little container will expand to 43.6 cubic feet of vapor. So 1 gallon of propane will give us 43.6 cubic feet of vapor. And from yesterday, we know how many BTUs we can get out of a cubic foot of propane. Do we not? Do we not? Yes? No?
Yeah, 2,500.
2,500 BTUs per 1 cubic foot. So 1 gallon of propane liquid will give us how many BTUs?
Is that the 43.6?
That is correct. So it's about 109,000 BTUs. Yes? Okay. Excellent. So for 1 gallon of liquid propane, we can get like 109,000 BTUs out of it. Now, a BTU is much like a wooden match. A wooden match, if you strike a wooden match, the amount of heat released from a wooden match is really equivalent to 1 BTU. So you can see how 1 cubic foot, 2,500 BTUs, is like 2,500 match heads going off at the same time. So it's pretty explosive. Now we go back into, let's go back into screen share here. Liquefaction, okay, that was that one. The next one is liquefaction ratio of propane gas in metric. So again, you are going to expand 270 times. So 1 cubic meter of propane liquid will expand to 270 times its volume. So 270 cubic meters. Okay. So that's the liquefaction ratio for metric. So gas has this stored energy waiting to be used, right? Because it's flammable, it's explosive. This energy, this calorific value, is measured in BTUs per cubic foot, and we call this the calorific value or heating value. Both words mean the same thing. I will use both words to describe these gases at any given time so you understand what that is. So the stored energy is released as we burn this fuel. And this energy, mostly heat, can be transferred into space heating or water heating or whatever purpose that we want it for. There it is, the amount of heat energy to raise the temperature 1 pound of fresh water 1 degree Fahrenheit, and that is the definition of a BTU. Do not forget that. It should not be new to you. The next part, alternatively, we use the name for calorific value is expressed as BTUs per imperial gallon of liquid. Here we go. BTU per cubic foot, methane 1,000, propane 2,500, butane 3,200. We know these numbers already. This is a little bit of a review. And here in this table, it gives us the kilojoules per cubic meter. So this is the metric equivalent. We will be mostly concerned with imperial measure. Mostly imperial measure. Now, if you notice, your gas code book is mostly imperial measure, but it always has the metric equivalent in brackets. Okay. Okay, I'm just going to share my screen again here. Just where we left off, calorific values of gases. There they are. We know these already, right? Methane is 1,000 BTUs per cubic foot, and propane is 2,500 BTUs per cubic foot. And then we have calorific gas values of liquid petroleum gases down here in this table. So calorific value of 1 imperial gallon. It says natural gas 9,600. Now listen, we don't deal with natural gas as a liquid for the most part, so we really don't need to concern ourselves with that. We have this commercial propane, 109,560. Now here is a little bit of a disparaging difference, because did we not calculate 1 imperial gallon to be 109,000 even?
Yeah.
And now this is telling me it's 109,560. So there's just a slight variation in that. I do want you to remember this number, the 109,560 BTUs per cubic foot. This is the number that you will find in the back of your code book. Remember that properties table in the back of the code book? Yes, we saw that the other day.
Was that the page 255?
That is absolutely correct, Brittany. Yes.
So Doug, because our numbers are different from what we said, is the 560 like a huge difference, or
It's not a huge difference, but that's the number I want you to know from 1 imperial gallon of propane liquid.
Okay.
1 imperial gallon of propane liquid will give you 109,560 BTUs.
So this is like the 8th rule, where the 8th doesn't really matter, that you're outweighed by an 8th, you're still good?
It's close enough, is what you're trying to say?
Yeah,
Close enough? Yeah.
An 8th to the 8th god, you know?
Yeah. Close enough without going over. The price is right, you know? All right. Let me go back to sharing. Here we go. Okay, we got that number now, 109,560. Excellent. Next. Oh, look at this guy. I don't. Why is this guy in our gas class? He's too old to be a plumber. Did you know that Albert Einstein, as a side note, wanted to be a plumber rather than a physicist, because he thought it would be easier. And
Did you ask him that personally?
No, this is true. This is a true story about Einstein. If you look him up, he said he would have rather been a plumber than a physicist, which probably would have been detrimental to the world. But anyways, just
Joke's on him.
as an aside note. Okay, we're going to calculate various trade-related problems using properties of gases. Whoa, there he is. Okay, so all gases and all gas appliances have a input rating. Okay, they're given an input rating. The manufacturer will come up with this number, how many BTUs that appliance will consume in a specific amount of time. And the time is always hours. So that appliance should never consume more than that maximum. And it is our job as plumbers and gas fitters, or gas fitters more specifically, that we have to verify this input value for this appliance. Because if this input value is exceeded, then that appliance has a chance to burn down to the ground and cause damage and maybe even kill people. So part of our job as well when we install an appliance is that we must verify that this appliance is burning that input value. As you can see in this little picture, it says input BTUH 34,000. So that is the maximum input that this appliance is allowed to burn. And we never want to go over that, ever. So again, the appliance manufacturer will only give you the energy consumption of the appliance after combustion. So we can verify how much this appliance has consumed, measuring the cubic feet per hour that goes into the appliance. Okay, it's before the combustion. It's how much gas is flowing in the pipe into the appliance. Okay, so to do this, we need to know some mathematical calculations, and we're going to figure some of this out. So we were also taught, though, that there's two types of fuels that are readily used in Alberta, right? Propane and natural gas for the most part. We don't use a lot of heating oil here in Alberta. In other parts of the provinces, East Coast, West Coast, they use still heating oil. It is the same input values, but it burns much differently. So we're not going to talk about that too much till fourth year. So listen, we're allowed by law, you and I, as gas fitters, to convert an appliance from one fuel to the other. But we also want to get approval from that. And the approval is from the authority having jurisdiction. Okay, so it's a safety codes thing. It is an inspection thing to do that. So when we do convert any appliance, that specific input value does never change. Let me emphasize that again. The input values do not change if we change fuels. A 30,000 BTU barbecue on natural gas is going to be a 30,000 BTU barbecue on propane. The input values never change for that appliance. Okay? There's other things we do have to change, but the input value has to remain the same.
And that's just on slide 44. You want us to make that note?
Sure.
Awesome.
And we'll talk about conversions later on and how much that is. So, now the only way to verify you've done your work properly will be to measure the gas consumption. Okay? Only when the appliance is running. How else are we going to do that? We have to have the appliance running if we want to know how much gas it's consuming. So if I look at the tables on the calorific values, you will notice that propane is about 2.5 times more than natural gas, right? Natural gas has a calorific value of 1,000 BTUs. Propane is 2,500. So it's 2.5 times more. But in the other hand, it's going to burn 2.5 times less gas than a natural gas appliance because it has a higher heating value. Does that make any sense to everybody? Is that clear? Yeah.
Wouldn't that change the input though? If it's burning, like if it's got more energy, wouldn't that change the input?
That's a great question, Ferd. So if I had 100,000 BTU per hour natural gas appliance, yeah, how many cubic feet of natural gas is that?
$100.
That's right. So if I had 100,000 BTU appliance burning propane, how many cubic feet of gas is that?
40.
Exactly. So we're using a lot less gas to get to the same heating value. Okay, that's all we're trying to do is compare propane to natural gas. So propane, I'll use a lot less propane to get the same result as I would for natural gas. Okay, that's all. And we'll do some math according to this at some point here. Okay, so all appliances have these efficiency ratings. Okay, they will have an efficiency rating. And you see in this little yellow energy guide thing, they have something called an annual fuel utilization efficiency. And you can shorten that word down to a FUE, A-F-U-E. You can make a note on your paper or wherever it is, A-F-U-E. A-F-U-E, annual fuel utilization efficiency. That is going to come up again. Okay, so that's why I want you to make a note. We're going to have that come up at one point again in our future class here. So listen, any appliance that uses any fuel source is not going to be 100% efficient, which means if I had a boiler and I'm burning 100,000 BTUs, all of that 100,000 BTUs is not going to be put into the water. We're going to be losing some BTUs out of jacket, stack, losses, whatever. It's not going to be 100% efficient. And this is where that efficiency comes into it. It's where how much energy is actually being put into the product we need, like the hot water or the heated air or whatever it may be, okay? For any space heating or water heating or whatever. So this input is, the input value is how much the appliance consumes, but then once we add the efficiency to it, we will find out how much is actually going into the water or to the air, because we will lose some. Okay. So we also may need to know how long an appliance will run to heat a certain amount of water. So it takes 1 BTU of energy, right, to heat 1 pound of water 1 degree Fahrenheit. So using this formula, we can mathematically figure out some stuff. So what I'm going to do.
Does the statement of fresh water there matter at all, or is
yes, it does, because it has to be fresh water because everything is compared to fresh water, right? Let me just open this whiteboard.
Fresh water just meaning desalinated, or?
Well, let's just go with what comes out of the tap. How's that?
Okay.
Okay.
But not the hot water tap, right? As we learned yesterday. The hot water tap is dangerous. The cold water tap's good.
Well, for you, Riley, the hot water tap is dangerous. I wouldn't use hot water if I was you. I don't know your capabilities.
I'm not gonna melt. Get out of here. Wish I
Is it
did.
because like stuff like salt changes the boiling temperature?
It does. Absolutely, it does. it has a different density, right? So the density that we want the water to be is fresh water, because we want it at our 62.4 pounds per cubic foot. We want it at standard temperature at 60 degrees Fahrenheit. That's all. Here we go. Okay. We're going to do some math. We're going to do some examples of math. The examples are in the PowerPoint, but I'm going to do them actually on the whiteboard that I have here. Okay. So let me just share this screen. So this is the formula we're going to be using. Let me just get a different pen here. Get a black pen. This is the formula we're going to be using for this. Let me get a triangle here where we have the heat and we have M, we have delta T, and we have SHC. And we're going to talk about every one of these. So this formula triangle is for sensible heat. When I'm talking about heat, I'm talking about BTUs or kilojoules is the heat. Okay? Mass over here, that's the M. M is equal to mass. The mass always has to be either in pounds or kilograms. Always, always. The delta T over here, this is delta T. So delta T. And this is the temperature difference. This is the temperature difference between the substance start and finish. Difference. Okay, between the start and the finish. And for example, if I had something that started at minus 10 degrees Fahrenheit and went to 32 degrees Fahrenheit, the delta T between these two is actually 42 degrees is the delta T. So you can see it's the differences in temperature from start to finish. This over here, specific heat capacity. So this is a specific heat capacity. And this is by experiment. They came up with these numbers. And this is the amount that a substance can absorb heat. So water has a specific heat capacity of 1 BTU per pound per degree Fahrenheit. Ice has a specific heat capacity of 0.5 BTUs per pound per degree Fahrenheit. And steam has a specific heat capacity of 0.5 BTUs per pound per degree Fahrenheit. I'm going to get back to this in a second. I think everybody has done this before. Yes? Everybody knows these numbers from the past. And if you did second year not that long ago, you will know that we cover this in second year math. Okay? So we're going to continue on. We're going to do these examples together and we'll get through it. So, for example, let me just move this up a little bit or over. How many BTUs are required to raise 1 pound of water 10 degrees Fahrenheit? How many BTUs does it take?
10 BTUs.
That's right. So if we use the equation, sensible heat equation, the mass is 1 pound multiplied by a delta T of 10 degrees Fahrenheit multiplied by the specific heat capacity of water, which is 1 BTU per pound per degree Fahrenheit. And as we go through this, look, the pounds get canceled out, the Fahrenheit gets canceled out, and I'm left with BTUs, and that is 10 BTUs. Very good. Now, how many BTUs is required to raise the temperature of 10 pounds of water from 100 to 110 degrees Fahrenheit?
Is it 10? Because you're just going up 10 degrees? Because 10 times 1 is 10?
10 pounds is my mass. Multiply by the delta T. 10
It'd be
degrees
100, wouldn't it?
Fahrenheit.
10
100.
times 10 times 1.
Yeah, that's right. There it is there. Okay. Now, how many BTUs? Another question. How many BTUs does it take to raise the temperature of 10 gallons imperial of water from 140 to 200 degrees Fahrenheit? How many BTUs?
Would it be 6,000 BTUs?
Maybe. So first off, we need a mass. We have 10 gallons. We know that 1 gallon is equal to 10 pounds. So we have 100 pounds of liquid. So there's our mass, 100 pounds.
Delta T is 60.
The delta T is 60 degree Fahrenheit, and we multiply by water, 1 BTU per pound per degree Fahrenheit. And that equals
6,000 BTUs.
beautiful.
I like it.
Very good. Excellent.
T.
Okay. How many BTUs? We're continuing on with more examples. How many BTUs in 125 cubic feet of CH4?
$125,000.
That's right. So we take 125 cubic feet, multiplied by the calorific value, 1,000 BTUs per cubic foot, and they cancel out to get you 125,000. Very good. Okay. We got that. We got that. Okay. So here's a new formula. Well, it's not new, but this is our efficiency where output divided by input would be my percent efficiency. Okay. So if I had an appliance that burned 180,000 BTUs per hour, and I told you that this appliance was 78% efficient, what is my output? And the output is how much BTUs is putting into the air or the water or whatever it is.
It'd be 126,000.
That is correct. So we take 180,000 and multiply by 0.78. So when you have a percentage, you divide it by 100 to get your multiplier of 0.78. And you said that was how much? 126?
Correct.
140. I got 140,400.
Oh, we have a little error there.
Oh, yeah,
140?
I just typed it again. That's what I got to.
Okay. 140? What?
140,
400.
144,000 BTUs. So we only actually have 144,000 BTUs going into our water if it's a boiler. Okay. The rest is lost through jacket and stack and transmission losses. Okay. The rest is lost through all of those things because nothing can be 100% efficient. It's very.
Doug, I'm
good.
getting 140,400.
Yeah. You
Uh,
just
oh,
misplaced
I
the
have
zero.
this 0
It was the operator
and this
error.
0.
Yeah,
Okay.
it's just
I should
Doug
stop
error.
relying on you, is what I'm saying? No.
Or
Well, you're
you know,
the operator.
Okay, sorry. 40,400. You guys said that. I just typed it in wrong. I'm a little dyslexic this morning, I guess.
that's some timers is showing. Maybe you needed more eggs.
I need something, and it's not eggs.
Well, you're not allowed your Coke until after lunch, so
Cocaine? Woof. Only kidding.
Coca-Cola. Coca-Cola, Doug.
Coca-Cola. That's right. Okay.
we're recording this, Doug. You might want to edit that out.
I don't think I will. Somebody's got to watch it for like 30 minutes to even find it. So good luck. Okay. What would be, let's have a look. So if you had a 100,000 BTU appliance and it is 80% efficient and it's burning, come on, quit pressing that button. Burning C3H8. How much cubic feet? I will change that. How many cubic feet of C3H8 will, this is for hour, you burn in 3 hours?
120 cubic feet.
In 3 hours? Excellent. That was pretty quick.
What?
Sure.
C3H8 is propane. Propane is 2,500 calories per, 2,500 BTU per cubic foot. 40 cubic feet per hour. 3 hours, 120.
That's right.
But aren't you just, don't you already have the BTU and then you're getting 80% efficient?
Well, listen, I didn't say anything about this. This is extra information.
Write
I
it
said,
down.
how much will you burn in 3 hours? So that was correct. We have the 100,000 BTUs per hour divided by 2,500 BTUs per cubic foot will give us 40 cubic feet per hour times 3 hours. We will burn 120 cubic feet C3H8. I just threw this in to try and confuse it, but somebody was too fast for me.
Yeah, and somebody got confused.
Somebody's doing the math faster than I could write it down. I don't even know how that happens, but there we go.
I'm not gonna lie, I got confused as well.
So questions will be posed to you like that, where there is different, distractors, I guess they're called.
There's no distractors in real life. It's I need this installed here. Do it.
Thanks for that, Riley. Okay, let's see what else we can get into.
What'd you order from the kitchen there, Doc?
Nothing. It was just my microphone wire fell down. Okay, here's a question for you. Let me just put it over here. There you go. How many hours would an appliance with an input of 50,000 BTUs per hour operate if 1,000 cubic feet of CH4 was burned?
20 hours.
Well, that is correct. Well, you guys are too fast for me.
Not me. They're not too
20
fast.
hours?
20 hours is correct.
How?
I just saw it from the ILM on page 17.
Oh, well,
Wow,
you
what the
go. Come
fuck?
on. I want you to do the math.
So you would
So-
take the 1,000 feet times it by 1,000 calorific value, gets a million, and then you take the million divided by the 50,000 BTUs per hour gives you the amount of hours.
Well, I would do it this way. I would take 50,000 BTU per hour, and I will divide it by 1,000 BTUs per cubic foot. That's the calorific value of CH4. Will give me 50 cubic feet. Cubic feet of gas of CH4, and then I have 1,000. I have 1,000 cubic feet to burn, and divide it by, this is per hour, right? I will divide it by 50. 20 hours. And they cancel out. So yeah, could you do it another way? Sure. I'm not going to dispute that. But here is that way. Okay, we're good so far? Excellent. That's going to be easy. Here we go. Here we go. We got a new question here. And don't look ahead, Farid. We want to do this. I'm going to change the numbers. Okay, I'm going to change the numbers on here so we can't cheat. So I got a hot tank, hot water tank.
Did you dress it up? That way it's hot.
Yeah, it is. It is 40 US gallons. Okay. And the incoming temperature of that water is 48 degrees Fahrenheit. And I want to know how many BTUs does it take to raise the temperature to standard settings. So take a minute and try to figure out how many BTUs does it take to get this tank to standard.
I think I've got it.
Okay, put it
Standard-
in the chat. Don't
Okay.
say it out loud. Put it in the chat. But when you got an answer, throw it in the chat. No, I don't think so.
Doug, is the standard temperature 15.5? Or
What is the standard setting for a hot water tank? Do you know that?
Standard was 140, wasn't it?
That's right. Standard. Brett, Kyle, that is correct. Josh, correct. Braden, correct. Matt, no. Toslin, no. Wait a second. Josh, looks like you're off by a decimal. Oh, wait, you're off by a little bit. No, it's not a 12-degree delta T. It's a 92-degree delta T. Josh, you're wrong. Ben, you're right. There you go. Fareed, you're off a little bit there. I don't know why.
Sorry, Doug, are you saying that I'm off or the other Josh is
Josh
off?
Hansen.
Oh, okay.
Sorry, Josh. Josh is deep. That is correct. No, deep, you're off too. I don't know why. Here, hang on a second. So we need a mass times a delta T times the specific heat capacity. So our mass, we have 40 US gallons. So we have to get a mass from that. There is 8.33 pounds in a gallon. So our mass comes out to 333.2 pounds. And then we multiply by our delta T. Our delta T is from 140 minus 48. So that's, how much is that?
92.
92. So we multiply by 92 degrees Fahrenheit, multiply by the specific heat capacity of water. And that comes out to 30654 BTUs. 30,000. Okay. Yeah. There you go. Peter, right. Yeah. Sean, D. Okay, good. Good work. We got that. Here we go. We're going to do a bigger question here. Are we ready for another question? Sorry. Can I move that over? Yes? No? Maybe so? Okay, just let me know if I'm going a little bit too fast. I could definitely talk slower. Okay, we have another question for you here. We have another hot water tank. I have a hot water tank that has 60 imperial gallons. Okay. And it has an input rating of 25,000 BTUs per hour. And that's my input rating. Okay. I want to know how many cubic feet propane and how many cubic feet of nat gas, okay, C3H8 CH4, to raise the water. Okay, hang on a second. I want to raise the temperature of the water from 35 degrees Fahrenheit, and I want to go to 150 degrees Fahrenheit. I'm just doing this for math, so nobody talk to me about over the limit here. But this appliance is also only 80% efficient. So I want to know these two things. How many cubic feet of propane and how many cubic feet of natural gas with this information that you have. Put it in the chat when you have your numbers. Okay, so we have this question here. So first off, I got to find out how many BTUs it does take to achieve this. So this is a sensible heat equation where we take our mass. So we have 60 imperial gallons. So we have to get a mass out of that. It's 10 pounds per gallon. So we have 600 pounds of water. And then we're going to multiply that by my delta T. So my delta T is from 150 and 35. So I have a delta T of 115 degrees Fahrenheit. Multiply that by the specific heat capacity of water. 1 BTU per pound per degree Fahrenheit. So let me just type that in. So that's 69,000 BTUs. So it takes 69,000 BTUs to heat that water to 150. But wait a second. I said that this appliance is only 80% efficient. So which means this appliance is 25,000 BTUs per hour. And if I multiply that by 0.8, this appliance actually, the amount of heat going into the water is actually 20,000 BTUs per hour, only going into the liquid. So now I can find out how many hours that is by taking my amount of heat required to get to that temperature, divide it by 20,000 BTUs per hour, and that will give me, I think, 3.45 hours. So that's how long it takes to heat that water. So now, if I go 25,000 BTUs per hour, and I multiply that by 3.45 hours, it gives me the total number of BTUs consumed of 86,250 BTUs is consumed to heat that water. And if I want to find out how many cubic feet of natural gas that is, divide by the calorific value of nat gas, that's 86.25 cubic feet of CH4. And I could do the same number, 86,250, and divide it by 2,500. 86,250 divided by 2,500. And that gives me 34.5 cubic feet of C3H8. So I don't know where our numbers, we got a couple of little disparaging numbers on here. And this is where we left off. Hopefully everybody has this down, and we're going to go into combustion, or identify definitions specific to combustion. Here we go, objective 4. So definition in combustion is as follows. It's really a self-staining process once you start it. The temperature liberated by combustion will be maintained above the ignition temperature. Okay, it's a kind of a chemical action going on here where we're burning hydrocarbons. So the definition of ignition temperature is as follows. The minimum temperature required before combustion can occur. So we need a certain point of heat. And that's what ignition temperature really means. So here's our ignition temperature for some of the common gases that we use. As you can see, propane And natural gas, okay, natural gas has a 1200 degree ignition temperature. So you could have a natural gas leak as long as you have a temperature of less than 1200 degrees around, or no source of ignition like a spark or a open flame. It will not combust. Okay, so these are ignition temperatures of common gases. So the definition of flame temperature is as follows. It's just the maximum temperature reached inside the flame, and the hottest part of that flame is just above the tip of the inner cone, right here where it has it heat of combustion concentrate at the tip. So the coolest part of the gas flame is at the base of the inner cone. Let me reiterate, it's going to be hot if you touch it, okay? You won't be able to tell the difference with your finger what is hotter and what is not hotter, all right? So don't stick your finger or anything
just the
else in
tip,
there.
right? Just the tip, right?
Don't even touch it with the tip, because, you know, you're going to get burned. You guys are funny. This is recording. Okay. I'm going to share my screen again.
No fear.
Okay, so that is the definition of flame temperature. And then we're going to give you a list. Here is maximum flame temperatures according to some of the gases that we use. Okay, natural gas, butane, propane. Those are just some of the maximum flame temperatures listed there. This is right out of the ILM as well. For those of you who are following this PowerPoint through your ILMs, does it match pretty closely?
Almost like bang on, yeah.
Bang on. Excellent. Thank you for that, Danica. And it is, and it should be. All right. So this is me going through the ILM with you. How's that?
This is awesome, actually. This is way better than just like you just reading the ILM.
I don't want to read the ILM to you, Danica. That doesn't help.
Thank
What,
you.
you don't want to read to us? I thought that was
Well, I will, but not always. I mean, you know. Did you hear that they put Dr. Zeus? They took a few books out of circulation.
I don't want to talk
It's
about
literally the biggest bullshit ever.
I don't want to talk about
Okay, flame temperature is not related in any way to the calorific value. Okay, so don't associate that. So if 1 cubic foot of natural gas is burnt, 1,000 BTUs of heat energy will be released. Okay, this will not change if the flame is normal, carbonizing, or oxidizing. And we should have learned what carbonizing is, and we should have learned what oxidizing is comparatively to what flames are. Carbonizing, fuel rich. Oxidizing, oxygen rich. Okay, one or the other. Flame speed. Okay, flame speed definition is the speed that a gas flame will burn. Okay, along a stationary column of combustible air gas mixture. So that's just the how fast things burn, and I think we even have a table for this. And not yet. Flame speed is also known as the rate of flame propagation. So listen, the whole volume of air and gas will not ignite at once because you need those air gas mixtures to be right before it will combust. And if flame burns through a stationary column of air and gas mixture of 1 foot per second, the flame speed is 1 foot per second. This is not hugely important. It is part of it, but it's not completely important for us. And I know why we have this going on. So, having said that, the general requirement for burners is required to move through the burner port at the same speed as the flame moves back through the air gas mixture. Okay, we want to stabilize flame at the burner points. So if we have the flame rate of propagation too fast, you will have a little bit of lift off. If it's too slow, you will have burn back inside of the burner. And here is the table for rate of flame propagation. Flame speed. All right, that's super interesting.
Is that
Okay.
something that we're going to have to know the numbers for off
No,
by heart?
I'm not going to ask you to remember those numbers.
Okay.
Okay, but you should know where to find them if you're asked about them. Okay?
Okay.
All right. So liftoff. This occurs when the air-gas mixture moves forward faster than the flame speed. Okay, you can have liftoff off the burner. Now, if you recall when we were in, or maybe you weren't, but in one of our shops where you had to light a torch, oxy flame, and if you had that acetylene set too high, you had flame liftoff from the end of the burner, right? Or end of the torch tip. So this is when that flame is above the burner ports. It happens in appliance, and this is where flame speed is a little important. We want to get it right, okay? And so here it is here. And then again, flashback occurs when your air-gas mixture moves more slowly than the flame speed, and it will burn backwards because it has the proper air-gas mixture below the burner. So it'll burn down there. And we don't want that to happen. So this is just a little indication of how that looks. I don't even know how somebody got that picture, but there it is. Range of flammability. So these numbers are the upper and lower explosive limits of the gases that we use. And this is where that gas will ignite. So for natural gas, it says a lower limit of 5%. This is the percent of air gas mixture that we need for combustion. Anywhere between 5 and 15% air gas mixture, you can have combustion. Anything below that, you won't. Anything above that, you won't. So we need to maintain that range of flammability when we're burning these gases. Okay. So that's the upper explosive limit and lower explosive limit. And so they are lower explosive limit and upper explosive limit. They have these little 3-letter acronyms. Okay. The lower limit of flammability is the minimum percent. Okay, this is just what I just said. I was a little bit ahead of myself on this one as well. I guess I know it, but I forgot what was in the next slide. Okay, so pretty straightforward. Any questions on this? I just want to reiterate that in a cloud of propane gas, if you are sitting in a cloud of propane gas, if you don't have those limits, the lower limit or the upper limit available for air, you will not blow up. Okay? You have to literally have those air to gas ratios to have combustion. Okay? You won't have combustion unless you have it. Next slide. We still talk about the upper explosive limit. This is fuel rich and referred to as a carbonizing flame, right? When we have a lot more fuel. Oxygen rich if it's the other way. Okay. Straightforward. And here we go. Based on an air gas mixture in which the air consists of approximately 20% oxygen, 80% nitrogen and other gases, there's a range in which you will have combustion. Next. Wow, we're still on this? Okay, so this is the smelling of gases. This is what they're talking about here. Requirement that a concentration of 1% gas be detected by a human nose, so to speak. Okay, so anytime you have a gas leak, you should evacuate. If you go into a building and you smell gas, Your job is to get people out of the building and then investigate the gas leak, right? Because you may be a source of ignition for that gas leak. Even don't turn anything off, don't turn anything on, just get out. Of course, for combustion, we need the fire triangle: oxygen, heat, and fuel. Those are the three things that are required for combustion. Combustion is the rapid oxidation of a fuel accompanied by the production of heat and or light. It says heat or heat and light. So heat and or light. Okay? So it's a rapid chemical union between the oxygen, the hydrocarbon, and then the heat. Okay? But in order to gain satisfactory combustion, basic requirements, we have to get the right mix. And once ignition has occurred, enough heat must be created to sustain that burning process, and in order to have a fire, the proper fuel air gas mixture. Okay, that's all it says. Boy, they repeat themselves a lot in these slides, eh? Chemical reaction between fuel and oxygen. When hydrogen burns, water vapor is produced. So these are the principles of combustion. This what happens. The complete burning of carbon produces carbon dioxide. So as you can see, we have oxygen, we have methane, and well, there's just carbon and hydrogen. And when you combust it, the products of combustion are carbon dioxide and water vapor. That is the result we want, is carbon dioxide and water vapor on the products of combustion. That's all we want. Fuel gases such as natural gas and oxygen react. Water vapor and carbon dioxide formed by that burning is called resultants, products of combustion. Okay, we just talked about that. I don't know why we're repeating ourselves over and over again. But here we go. This chemical formula right here shows complete combustion or perfect combustion or stoichiometric combustion is perfect combustion. So it's methane, oxygen, and ignition will produce carbon dioxide, water vapor, heat, and or light. Heat, light. Okay? Pretty straightforward. You should know this perfect combustion formula that is in here. The CH4 plus 2O2 plus ignition is equal to CO2, 2 H2Os, heat and light. So, objective 6. Oh, we're getting close. We're getting close. List and describe the products of complete and incomplete combustion. So, air is 80% nitrogen, 20% oxygen. And here is a little pie chart of air and what air is. So look at carbon dioxide, 0.03%, other gases, argon gases, etc. Yeah. So nitrogen is an inert gas, and therefore it passes through the combustion process unchanged. So that's why it wasn't listed in the previous perfect combustion chemical formulas. Okay, because it goes in and out. It doesn't have an effect on anything. So there we go. We added the nitrogen on this products of combustion, and it just goes through. So you see the 8 N2s, because it's 80%, air is 80% nitrogen. Oxygen is 20, or there's 20% oxygen in air. So there's the 2 and the 8 to make up 100%. Everybody see that? Okay. And that's how they do this. So 1 cubic foot of methane is equivalent to 1,000 BTUs, then 10 cubic feet of air is required for each 1,000 BTUs, and that's theoretical air. Remember we talked about that yesterday, theoretical and excess. We'll maybe talk a little bit more about that, I'm not sure. There we go. So type of gas, natural gas, 1 cubic foot of gas, 10 cubic feet of air. Propane gas, 1 cubic foot of propane, 24 cubic feet of air. We went through this already. So any questions on this? Just shout out if you do have something. Okay, so here we have the products of combustion. So combustion air requirements are the amount of air theoretically, we talked about that before, for combustion. And in theoretical air, we have primary and secondary in the theo air. This is not talking about our excess, in excess of. It's just talking about theoretical air. And here we go. Combustion air enters the bottom with gas, then rises through the flue, etc. So this heater, it's 2,500 cubic feet per hour of natural gas. So times that by 10, you're going to have 250 cubic feet of combustion air per hour. That's primary and secondary. Now, we didn't add excess air to this, so just hold on that one. Excess air is 40% of theo air, and that doesn't show it here. So, to ensure you achieve complete combustion, primary and secondary plus this excess air is part of the air supply, and we did talk about that yesterday. And you could always review that. I posted the recording on your air supply and venting D2L shell. Listen, we always want the flame on the burner to look as blue as possible. This is a visual assessment of the flame as a gas fitter. You will have part of your maintenance is to look at this flame to see if it's blue, and it needs to be blue. And if it's not, we need to fix it. And we can fix it by adding more air or reducing the air, etc. Okay, so not enough air is supplied, incomplete combustion will take place. And incomplete combustion of these products are harmful, especially carbon monoxide, CO. Carbon monoxide, and as you can see down here at the very bottom left, or right, my right, very bottom right, carbon monoxide can produce some deathly effects. So aldehydes is some of the other products of combustion. They have a sharp penetrating odor. They will actually burn a little bit as you breathe them in. They'll burn your nose kind of thing. Okay, so you know that may be around if you could smell that. Okay, so supplying enough air may not always guarantee that complete combustion has taken place. So we kind of want to see that flame for the most part. And there we go. So if you have a flame that's called, you see this flame? It's touching this metal up here. This is called impingement. Okay, when the flame is impinging on another piece of metal or whatever it is, it means it's touching, it's impinging on something. What can happen is you can produce soot, you can produce carbon monoxide, you can produce the aldehydes. Okay, so you don't want to cool off the flame through impingement on other things. So we want to make sure that flame is burning freely and blue and not impinging on any materials. So when you do not have enough air on a flame, you will get this lazy yellow color will appear. And this kind of flame produces carbon monoxide, carbon, in the form of soot. A black soot will form from this. And this is incomplete combustion, for sure. Incomplete. Okay? So what we'd have to do here is we simply have to add more air. If you have a lazy, luminous, yellow flame, luminous meaning bright, yellow, you will have to add air to that burner before ignition to get it to a blue flame. So poor appliance venting can also cause incomplete combustion. As you see in this picture right here, this is a draft hooded furnace, excuse me. And this drafted, you see where the products of combustion, you see how they have this arrow coming out. That is a backdraft. The actual air should be moving upwards. The air should be moving, it should be moving this way up. So you could always do a match test. I can't believe they have a cigarette there. You can do a match test to see if you have proper draft, meaning that the smoke here from this should be going up into the draft hood and out the vent. Okay, so that is a little bit of that. Okay, so you could do a quick check to see if this appliance is back drafting. And this is a dangerous situation. If this appliance were to fire, all the products of combustion would be pushed into the building or the room that this is housed in. And that would be a problem. So in addition to being harmful, carbon monoxide also lowers the efficiency of the gas burning appliance. First, heat output to the fuel is low due to incomplete combustion, and then unburned carbon will eventually line the walls of the heat exchanger and act as an insulator. And guess what? Carbon monoxide is also flammable. Okay? And so if you've ever seen the movie Backdraft, where they have a closed room and the fire is just smoldering, there's an ignition source there, but there's not enough oxygen. And as soon as they open the door, oxygen is able to rush in, and all of the fumes that are in that room are combustible. That's why it blows up. That's the reason for this backdraft, that explosion that happens. And if you see the carbon monoxide, the range of flammability is 12% to 74%. So it has a very high explosive rate. Doesn't take much to, it has a lot of range, so to speak. Okay, so products of combustion are flammable. So when a fuel gas is not completely burned, hydrogen gas can also be present. Hydrogen, while not toxic, can burn or explode in air, and it has a high flammability rate as well. A reduced yellow lazy flame is a good indication that there's not enough air to the burner. Okay, so this is a visual inspection. You can look at a burner of any sort on any appliance and say, that doesn't look quite right, unless it was designed to look like that. And we could talk about fireplaces, etc., and that's a little bit different. So carbon monoxide, odorless, tasteless, called the silent killer. And what happens is that the carbon monoxide is very sticky as it gets in your bloodstream, and it really sticks to the hemoglobin in your blood. Hence, you won't be able to get oxygen into that blood because these carbon monoxide molecules are taking the place of oxygen, and they're very sticky, and you can't get them out. And you can't get them out because of the stickiness, so you need to actually have oxygen pumped into your body to expel these. Because basically what you do is suffocate. And it's not fun. I have actually had carbon monoxide poisoning.